model this way.
Yeah, it'd be super cool. Yeah. Pierre likes it because it's a way to get from 8D to 4D. That's so he's thinking, okay, the interactions are happening up here, but we don't perceive 8 dimensions. So that's why he wrote a paper on mapping it down so he can actually see what's happening. But perhaps the scattering, of course, is way easier in 8D when you're doing it Piero's way. So you just have the commutators hitting each other. But down here in the quasi-crystal, you have all kinds of dynamics occurring. Right. Yeah.
There's nothing else.
Many of my physics colleagues will say that mathematics describes our physical reality, at least in some approximate sense. I go further and argue that it actually is our physical reality.
Told us light was a wave. So now let's fire photon particles, one at a time, at the slits. What happens is that for each photon, the detector registers a hit on the back screen at a single point. And at first, with a small sample, the hits seem random. But over time, we see that the interference pattern re-emerges. Here's a video of the detector plate. It's as if each photon was contributing to the interference pattern, even though there wasn't another photon to interfere with. So, the conclusion is that photons interfere with themselves. Turns out that they only interfere with themselves. They never interfere with another photon. Now look what happens if we detect which slit the photon went through. Here, a detector registers yes if the photon went through the upper slit, and no if it didn't. The detector sees a photon coming through the top slit around half the time. We assume that if a photon went through one of the slits and it was not the top slit, then it must have gone through the bottom slit. Here's the resulting pattern. But this is the pattern for particles. If we turn off the detector, we get the pattern for waves again. This duality this day. A good way to look at it is light propagating through space as a wave. But at any time it interacts with something, it interacts as a particle. In other words, it is created as a particle and absorbed as a particle, but travels through space as a wave. So it's important to remember, electrons in an atom do not orbit the nucleus. They are not like planets around the sun. They exist as stationary, standing waves. So physicists climbed mountains and went up in balloons with their cloud chambers, hunting for new particles. Here's what radiation looks like in a cloud chamber. The atmosphere in the chamber contains a vapor of alcohol. When charged particles move through the atmosphere, they cause little droplets to form. These are the cloud tracks that we see. It works on the same principle as tracks forming behind high-flying jet aircraft. In 1928, 4 years before Anderson discovered the positron, Paul Dirac predicted the existence of antimatter and proposed that all particles had antiparticles and that they would annihilate each other if they came into contact. The positron is the antiparticle of the electron. Here's an event in a cloud chamber that shows the creation of a pair of particles, one electron and one positron. This event was the conversion of a high-energy gamma ray that kicked an electron out of an atom and was itself converted into two particles. Now's a good time to review the particle sizes we've seen so far. In our first segment, we used an electron microscope to see a carbon atom with a diameter of 0.14 nanometers. That's 1,000,000 times smaller than the width of a human hair. In our second segment, we probed the atom with alpha particles and found that the nucleus was very small compared to the atom. Here we have the carbon nucleus at around 26,000 times smaller than the carbon atom. The simplest nucleus is hydrogen's. It's just a proton. Its diameter is 78,000 times smaller than the carbon atom. In this segment, we probed the proton with high-velocity electrons and found that it had 3 components called quarks. Powerful accelerators and hadron colliders have put the upper limit on the diameter of the cross-section of quarks at 1 times 10 to the minus 18 meters. That's 1,760 times smaller than a proton and 140 million times smaller than a carbon atom. This is also the upper limit for the cross-section of an electron. The neutrino is the smallest elementary particle, with a cross-section that is 1,000 times smaller than an electron or a quark. That makes it 140,000 trillion times smaller than the diameter of a human hair. In an atom. For example, a beam of photons can be made to have the same quantum state. This is how a laser works. On the other hand, the inability of electrons to fit into the same quantum state creates an outward pressure that halts a star's collapse. Our very idea of what a proton looks like has now shifted from a point particle to a 3-part particle to a whirlwind of elementary particle activity. In fact, it is very difficult to distinguish between the disturbances that represent virtual particles and disturbances that represent actual particles in a plasma like this. But for our purposes, we can view a proton as a cloud of gluons holding 3 quarks together. The proton is key to helping us understand the origin of mass. The only stable elementary particles in the proton with mass are the 2 up quarks and 1 down quark. Their tiny masses constitute only 1% of the mass of the proton. 99% comes from the energy of the fields and motion of the moving parts following the famous E equals mc squared formula. So it is quite accurate to say that confined energy is the origin of mass. We'll bring this point home when we get to the Higgs boson. And neutrons. As the distance between quarks grows to the diameter of a proton, the strength of the force approaches 18 tons. Imagine 18 tons focused on such a tiny spot. This makes it virtually impossible to separate quarks. All of space is filled with matter fields that can spawn fermion particles as waves. This includes all the leptons and the quarks. These particles carry one or more charges: color charge, electromagnetic charge, and weak hypercharge. Particles with a charge fill the space around them with a force field that can spawn force particles when excited by particles that carry their charge. These are the bosons. The bosons are the force carriers or mediators of all fermion particle interactions.